Now we're going to look at a more general idea about where we're moving with this calculus and this instantaneous rate of change. So now we have a car rolling down a ramp. And as you can imagine, a toy car that's rolling down a ramp, as it starts to roll, it covers more and more distance over time because of acceleration due to gravity, probably, and the incline here. It is picking up speed. It is picking up velocity as it rolls down this ramp. We can see in the first half second, it doesn't travel so far, but in that last half second, it travels quite far. And so what if I asked a question and I wanted to know, what is the instantaneous rate of change at, like, what is the speed at a specific instance? And so I could ask for the speed at exactly 0.5 seconds. What is the speed of this car? Well, it's pretty slow, but how slow? Well, what we could do is we can take what I have over here, which is the distance that it's covered over each of these seconds. So half a second it's traveled 28 centimeters, and 1 second it's traveled 69 centimeters, and so on. And I can create a little graph with that. And so what I did is I created a curve, a smooth curve, which hopefully should make sense, of the distance over time. And I want to know, what is the exact speed at this instant here at 0.5 seconds. Let me use black. Well, how do I find that exact speed at half a second? Well, what I can do is I could start by finding the average speed from 5 seconds to 3 seconds. So I'm gonna do that. The average speed from 5 seconds to 3 seconds is, I could find it up here. It's total distance, which would be 400 minus 28, divided by total time, 3 minus 0.5. So what was that? 400 minus 28 over 3 minus 0.5. And I have this already written down. It's about 149 centimeters per second is the velocity. Well, that's probably going to be much faster than it actually is at 0.5 seconds. So let me now, I'll choose another color, and I could find the average rate of change, maybe from 0.5 to 2.5 seconds. So that's 0.5 to 2.5. So these are all my average rate of change, average velocity. And this is not super neat, but I hope you can follow along. And I could use that same formula from 0.5 to 2 seconds. And I find that it's about 133 centimeters per second. Makes sense. The average here is going to be a little bit slower. I could do the same thing for 0.5 to, that one's 1.5 seconds. No, 2 seconds, from 0.5 to 2 seconds in blue here. And I found that average rate of change, I already found it, is 117 centimeters per second. I could do it again now for 0.5 to, what is that, 1.5 seconds. So from here to here, it's getting a little bit sloppy in green. And that would be 99. It makes sense. It's a little bit slower, centimeters per second. And then I could do it one more time for just the average rate of change in that half a second, from half to 1 second in gray here. And that's 82 centimeters per second. So I'm getting closer to the instantaneous rate of change as I keep finding the average rate of change to a time that's closer and closer to 0.5 seconds. So I started with 0.5 to 3 to 2.5 to 2 to 1.5 to 0.1 to, and then 0.5 to 1 exactly. And so how would I actually find that exact instantaneous rate of change? It's going to be a little bit less than 82 centimeters per second even. And you may have guessed, or maybe you know this already. I'm going to erase this and not make this another video. The instantaneous rate of change at a specific time, at a very specific time, is equal to the slope of the tangent line at that time. So let's go up here for a second. And if I were to draw the actual tangent line at this point, the tangent is, Again, a line that just grazes the curve at that one point. So it's the slope of the tangent line. It's a little messy. It's hard to see. At that point is the instantaneous rate of change. And that's probably your biggest deal with calculus right now, is understanding that if I wanted to find, for instance, the instantaneous rate of change on the red curve here, then I could draw this blue tangent line at that curve. It's tangent at this point. That blue line is tangent at this point. Sure, it touches the curve later on, but at this point it barely grazes it. And the slope of the blue line is the rate of change at that specific moment on the red curve. I suggest you write this down and draw a nice graphic in your notebook.